This is my old thermometer thermostat. It's very precise and efficient. It turns on this relay when the temperature exceeds a certain value. Look here, you can adjust the temperature threshold using these buttons. And this is a new instance. Let me test it using this slider and this fan. This is a simple but very efficient thermometer thermostat ever. I know there are countless videos of people making thermostats, so this video is not just about making a dry thermostat. In this video, I'm gonna teach you many useful points and techniques in the heart of a simple thermostat project. In this video, we are going to make this circuit, analyze every single component on the board and see why it is used there. We will explore PCB and schematic files as well. By the way, I will give you all the files needed to complete this project, including ATmega8 audio project, Altium Designer project, codes, makefile, etc. Please stay with me until the end of this video. Let's discuss this guy. It's so cute. There is a microcontroller on it for handling control process along with other components to do necessary tasks, a sensor, a display, a switch, etc. The main building block of any electronic device is its PCB. We have to design the PCB, build it and assemble components on the PCB to have a successful project. In the first step, it's so nice to look closer at the PCB, schematics and components used in the circuit and see how it works. This is the schematic diagram of the circuit and this is the PCB design. I have designed the schematic and the PCB using Altium Designer. The main process goes like this. This sensor measures the temperature and presents the temperature in the form of voltage on its output pin. The higher the temperature, the higher the voltage on the sensor output. Each 1 degree Celsius will be presented by 10 millivolts, so 25 degrees Celsius will be presented by 0.25 volts or 250 millivolts. The microcontroller is reading the sensor voltage continuously through the ADC unit and decide when to turn this relay on or off. The output voltage of this sensor may contain noise and this noise may cause problems. I have used 2 techniques to overcome the noise. I will talk about them later in this video. Anyway, the next thing is the power supply. In this project, I had decided to power the circuit up using a USB cable. The USB socket is this. The circuit here is super simple. I put a capacitor here as input capacitor and an LED which indicates existence of voltage on the circuit. Obviously, a resistor should be used in series with the LED. This is the programmer connector. These pins are connected to ground and MOSI, MISO, SDK and RST pins have been connected to corresponding pins on the microcontroller. Look here, there are similar pins on the microcontroller. MOSI, MISO, SDK reset pins. This is the corresponding PCB. It's a 2-layered PCB. The traces on top layer, look here, are drawn like this to make it easy to build the PCB at home. If you look attentively, you will realize that the traces on top layer are straight lines like this one, and this one, so I can use wires to form them. Look here, these wires are traces on the top layer. The bottom layer is built normally and to form the top layer I have used these wires. You can make the PCB yourself, which is a hard work, or you can send files to a manufacturer. Now I'm working with PCBWay.com. A big thanks to PCBWay.com for sponsoring this video and manufacturing such an admirable PCBs in really short period of time and at a reasonable price. You just need to sign up on PCBWay.com. It's easy and free. Then fill out this order form to see the estimated invoice price and then submit your order. After submitting the order, PCBWay agents will review the order and determine the exact invoice price. Then you are only one step away from your PCBs. You only need to pay the invoice and wait for the parcel to arrive. It's that simple. My PCBWay referral link is in the description. You can use my referral link to support me. Now I have these high quality PCBs and I'm ready for soldering components on them. I prefer to start with thin components like microcontrollers. This is the MCU I have used in this project, ATmega8 AVR microcontroller. It's the heart of the project and almost all the other components are connected to it. 7-segment display, relay, buttons, sensor, and others. It's placed here on the bottom layer. Look here. This is the MCU I have used. These are my ordered PCBs and there are some gifts from PCBWay.com beside my order. These are my ordered PCBs. They are nice, sharp, and well made. I love them. The first step is to connect the PCB to the PCB holder. This is an SMD packaged ATmega8 AVR microcontroller. I'm starting with this cute component. In the first step, I put some solder on one of corner pads and put the IC on its place. So I need to solder another pad on opposite side of the IC to make it fixed and steady. It's really important to solder two pads first on opposite sides like these two pads or these two to fix the IC on the PCB and then check if it is placed exactly in the desired position. Then we are ready to solder the other pads. The IC is placed in the correct position and now I'm going to solder the rest of pins. If the solder connects two neighbor pins like this, you can use the iron to solve the problem, and if it doesn't work, the soldering wick will work nicely. The next components are these resistors. These resistors are used here to restrict the amount of current flowing to the LEDs inside the 7-segment display. I'm gonna use 100 ohm resistors here. By using higher values, the display brightness will be decreased, and by using lower values, display brightness will be increased. Look here, those resistors are placed here. This one, this one, this one, these two, and these three resistors. I have stored many resistors here in this plastic jar, so I have to search for 100 ohm resistors here. Let me pour all of them on the table. This will make searching for 100 ohm resistors easier. After finding the desired resistors, it is time to solder them one by one. To solder each of them, I need to put some solder on one of the pads, then place the resistor in its place and solder the first pad, then the second pad. Be careful when soldering these tiny components because they are so sensitive to heat and you have to solder them quickly. Now this is the result. I have soldered all of the resistors and I'm ready to move on to the next component. The next components are these transistors. Look here. These are BC857 transistors and this is a single C945 transistor. This C945 transistor, which is an NPN transistor, is used here to trigger this relay. When the microcontroller is about to turn this relay on, it will put 5 volts on relay net, which is connected to port B0, and this is enough to turn this transistor and consequently turn this relay on. These BC857 transistors, which are PNP type transistors, are used to select the desired digit on the 7-segment display. When the microcontroller wants to show a digit on the display, it should turn the corresponding transistor on and then put the desired pattern on this port. You may ask why it is important to use a transistor here to put the source voltage on the common terminals of the display. Why haven't I connected these common wires directly to the GPIO? Because there are 7 LEDs on each digit. I mean LEDs A, B, C, D, E, F, and G. If all of them turn on simultaneously, they will draw high current from the microcontroller pin and it will damage the microcontroller, or in the best case, the brightness of the numbers displayed on the 7-segment display will vary from number to another. For example, number 8 will be displayed at the lowest brightness because the microcontroller pin has to turn on 7 LEDs simultaneously, but number 1 will be displayed at the highest brightness because it needs only 2 LEDs to display number 1. So I'm using these PNP transistors to protect MCU pins by reducing current on the GPIO and also to have a nice and a smooth glow on the display. These are BC857 transistors. I need 4 of them. To solder these tiny components, I have to put some solder on one of its pads, then solder the corresponding pin to fix the device on the PCB. Then I will be able to solder other pins in peace. I have to do same thing for each of transistors. Look here, I have soldered all the transistors. Now is the time to move on to the next component. The next component is the capacitor. There are 8 capacitors in the circuit. Look here, one of them is here. This is the power input capacitor, which is placed here near the mini USB socket. This is the capacitor I was talking about. Next capacitor is near the relay. I mean this capacitor, which is used to prevent voltage drop when the relay is turning on. It is placed near the relay. This is the capacitor I was talking about. Look here, this is the relay and this is the capacitor near the relay. Also, there are 2 debouncing capacitors here. I mean this one and this one. This is the debouncing capacitor for the first button and this is the debouncing capacitor for the second button. They are placed under the tactile switches. Look here, these are tactile switches and under each of them there is a debouncing capacitor. This is the debouncing capacitor for the first button and this is the debouncing capacitor for the second button. Also, there are 2 capacitors near the microcontroller. I mean this one and this one. These are bypass capacitors which are placed near the microcontroller. This one and this one. Also, there are two other capacitors near the sensor. I mean this capacitor and this capacitor, these are used to fix the voltage near the sensor and also to fix the output voltage of the sensor. They are placed near the sensor. This is one of them, and this ceramic THD capacitor is another one. This 100 nanofarad capacitor is this ceramic THD capacitor. Now is the time to solder these capacitors on the PCB. The process of soldering the capacitors is similar to that of resistors, but capacitors are more sensitive to it. The next component that I need to solder is this mini USB connector, which is placed here. This is the mini USB connector. To solder this component, I have to place the component in its place first and then solder its shell to the PCB to fix it, and then I will be able to solder its pins in peace. In the previous section, I forget to solder this capacitor. This is the result. Now is the time to solder bigger components. To finish the process, I will solder this relay, this terminal, this 7-segment display, this programming IDC, this LM35 sensor, these buttons, these THD resistors, etc. I'm gonna start with the programming IDC. It is used to make connecting the programmer to microcontroller easier. It has 10 pins. It is connecting the MOSI, MISO, SCK, RST and ground pins of the microcontroller to the corresponding pins on the programmer. This is a relay switch. Look here. This is a contact terminal and this is a C945 transistor to switch the relay. This resistor here is the base terminal current limiter resistor, and this LED here is the green LED on the board which indicates whether the relay is on or off. This diode here is a flywheel diode and it is necessary to use it like this here to eliminate the spikes of the relay when the relay is turning off. In short, this diode prevents the microcontroller from resetting and prevents possible damages to transistor which controls the relay. As the next part, I'm going to solder this relay switch. I'm gonna solder the relay. I have to put the device in its place and then solder pins one by one. Now is the time for the 7-segment display, I mean this lovely component. This is the 7-segment display schematic symbol. Actually, there are a lot of details about 7-segment displays and their mechanism of operation that are not covered here in this video because of the time restriction, but I will try to cover those details in one of my next videos. So, in this video, I assume that you are familiar with 7-segment displays. I'm gonna put the component in its place and start soldering its pins. Now it's okay. The 3-pin terminal is the next component I'm going to solder. It is done. Let's move on to the next component. There are two tactile switches or push buttons here, and I put a 100 nanofarad capacitor in parallel with each of them to remove bounces. Look here, this is the capacitor in parallel with this button, and this is the capacitor in parallel with the second button. If you wonder why I put these capacitors here, why they are necessary, and why I have used this particular value, I mean 100 nanofarad capacitors, you have to see the related video in the description. By pressing this button, the net Q1 will be connected to ground, and this button will connect the net Q2 to the ground. So you see, the net Q1 is connected to PB1 and the net Q2 is connected to PB4. PB1 and PB4 are defined as inputs to the microcontroller, and an internal pull-up resistor is activated on them by software. If you look a bit further, you will realize the net Q1, which is connected to ADC7, I mean the pin 22. Actually, it is not necessary for the system to work, but I have connected the Q1 to ADC7, I mean pin 22, to make me able to pass the trace through the ADC7 pin. Look here. This is the net Q1, which has to be connected to pin 13, but it is passing through pin 22, which is ADC7. In fact, connecting the Q1 to pin 22 makes the routing process easier and simplifies the PCB. I did the same thing here on ADC0. Look here, pin 23 is connected to ground, which seems useless. Why somebody should connect an analog input to ground? Because in the routing process, I needed to pass the ground net through that pin, I mean pin 23. Remember, I had decided to make the PCB myself. I had those considerations to make my work during PCB building phase easier. Now is the time for soldering the buttons. I'm going to use a piece of tape to fix the buttons in their place. After soldering one of its terminals, I can remove the tape and adjust the components in their place, and then I will be able to solder the other pin with ease. Now it's ready. In the next step, I'm gonna solder these resistors. This one, and this one. I mean these, and these. After finding the resistors, I'm going to put them in their place and stick them to the board using pieces of tape, then start soldering pins. This is the result, but my favorite part is still left, cutting extra leads. In the next step, I'm going to solder these components. This THD ceramic capacitor, this LM35 analog temperature sensor, this diode, this green LED, and a yellow LED instead of this red LED. Now that the soldering process is over, we are about to test the circuit. To start testing the circuit, we have to apply proper voltage to it by connecting mini USB connector to USB. But I prefer to do the first test using a power supply to see if the circuit draws normal current or it is drawing high current. I am doing this to see if there is a short in the circuit or not. The current drawn by the circuit is almost zero, so there is no short in the circuit. Now is the time to connect the programmer to the IDC connector, connect the USB and program the microcontroller. It's working just fine. Now I can remove the programmer connector and adjust the threshold temperature to 23 degrees Celsius using up and down buttons. If three lines are blinking in the first and second digits like this, it means that the number shown on the display is the threshold value, and if there is no blinking lines in the first and second digits, it means that the number shown on the display is the live sensor temperature. Now the threshold temperature is set at 23 degrees and the environment temperature is 26 degrees, so the relay and the green LED are turned on. Now that I'm heating up this sensor using the slider and increasing the threshold temperature to 30 degrees, the relay is still on because the sensor value is higher than 30 degrees. But if I wait for the sensor to cool down, the relay will be turned off when the sensor value gets lower than 29 degrees. See, the relay is turned off. There are 2 points left. The first one is to use a piece of dark colored PVC sheet to increase the contrast of the display like this. And the second one is a technique called the Schmitt trigger. This is LM35, a precision analog temperature sensor IC. When you apply proper voltage to VCC and ground, the IC starts operating and shows the temperature on its output pin. Everything seems okay, but you may realize a weird thing. The voltage on its output terminal can contain noise. This noise will cause the relay to turn on and off widely in this small and specific range of temperature. This is a big problem. There are many solutions to deal with this problem. I have used 2 of them. The first one is to use moving average of the sensor value instead of its raw value, and the second one is a technique called the Schmitt trigger. A Schmitt trigger is very simple and powerful and can be implemented either using software or hardware. In this project, I have implemented the Schmitt trigger in the software. The Schmitt trigger goes like this. Instead of having one threshold value, we have 2 threshold temperatures. The user determines one threshold, but we have to convert it to 2 thresholds. For instance, ordinary single threshold method works like this. If the user determines 30 degrees Celsius, they turn on the relay when the temperature exceeds 30 degrees Celsius and turn off the relay when the temperature falls below 30 degrees Celsius. No matter how much it exceeds or falls, 5 degrees or 0.001 degrees. So, when the temperature is near the threshold value, it may turn on and off the relay wildly because of the noise. In contrast, the Schmitt trigger method has 2 threshold temperatures. For instance, in this project, I have defined 2 thresholds. The first one is 1 degree higher than the desired temperature, and the other is 1 degree lower than the desired temperature. My code goes like this. If the sensor temperature goes higher than 31, then turn on the relay. If the temperature falls below 29, then turn off the relay. And if the temperature is between 29 and 31, simply do nothing. This method is called the Schmitt trigger. I wrote the code in ATmega Studio, and all files including ATmega Studio project, C files, make file, Gerber files, PCB, schematics, etc. are available at a link in the description. Anyway, we have reached the final moments of this video. I hope you enjoyed this video and learned something new. Thanks for watching. If you found this video helpful, please give me a thumbs up, and if you like this video, make sure to subscribe for more.